Is being recorded.
So good afternoon, everyone. Welcome to today's talk. It's a very important topic. I hope you are impressed with the topic, and that's why you are here, hopefully. Um, so, so just a quick question. How many miles do you think are needed to be analyzed for a self-driving car to be really operational? Self-driving car is all machine learning, right? So how many miles do you think, a rough guess, how many miles do you think you need to analyze before self-driving cars can really go into production?
10,000 miles?
10,000?
Billion?
Yes, billions of miles. And can you imagine how much time it takes to process billions of miles? Huge, right? So machine learning and artificial intelligence in general takes a lot of time, right? Computing time. But if you have noticed, a lot edge devices, like your Nest cameras at home, they do quite a bit of processing by themselves, artificial intelligence processing. So they can distinguish the people in your home from outsiders and flag a warning when people are strangers, and when it can't recognize known cases. So that's all an application of artificial intelligence. And it does it quickly. It doesn't send the stream to the cloud and then wait for the answer to come back. It processes the whole thing on the edge device itself. So today's topic is all about that. I met Rohit in one of the events, and I was really impressed with the work he has been doing in this area. So I thought Cisco should benefit from his insights into this really cool technology. How to bring artificial intelligence into the edge devices, which don't have a lot of power, computing power, but still be able to demonstrate some artificial intelligence capabilities. So that is the topic for today. So Rohit Sharma is a very well-known author, speaker, entrepreneur. He started two companies. He founded two companies. And he has been very active in the EDA domain. And he has more than 20 years of experience in the electronic design automation domain. He works for reputed companies like Cadence, Magma, and all. Now he's focused on artificial intelligence. He has a number of papers published in reputed journals and conferences to his credit. So without much ado, let us call the speaker to the stage and ask him to start giving us insights.
Thank you, Vishnu, for the kind words. So before I start, this talk is primarily just a conversation and to sort of give you an idea of what we have learned over the past year and what we are seeing as a trend. As a show of hands, how many of you have done at least one application on AI or machine learning? Machine learning. Okay, so a few. And how many of you, so what level of complexity on a level, just as a show of hands, do you think it's too complex to learn or is it easy to get started? So show of hands, sorry, let me clarify. So if you think it is too complex to learn and get started, raise your hand. Okay, nobody. So that's a good news. So my hope is by the end of this talk, I should be able to leave you at least with one application and how to run very quickly in seconds. And that will get you started and at least your interest and being able to deploy those models in whatever you're wearing today. There are ways that many of us do not realize that you could program your watches, your microcontroller power devices that we have on us, pretty much everything we do today. And these are under $20 components, as little as $1. So teeny tiny devices that are pretty much everywhere. If you are sitting in a car, there are 20 around you. And those are driven based on sensors. If you're wearing under $30 or $50 watch, there is one inside that. If you're watching TV, probably multiple. Refrigerator, washing machine, toys under over $20. So if you have things around you that run on battery, likelihood is that you have a microcontroller inside that. And this is not new, it's been there for over 40 years since these things started, and then CPUs took over, right? Now, so let's get started with my introduction. So yeah, thank you, Vishnu, for the kind words. And my background has been in EDA. I started in a startup, and I've been fortunate enough that inside EDA domain, I worked for 5 startups, and 4 of those got acquired. So I've seen, by the sheer luck of chance, most of the successes, where 90% of the companies fail. I have worked for large companies too, TI, Cadence, as part of acquisition. But I've enjoyed the startup world way more than large companies. And I've been married, I've been stayed in the area for almost 20 years. 2 kids, high school going, very curious, enjoy their company. So now to the topic, why AI? I'm sure you guys know, in the media, everybody's talking about AI. And one of the reasons is it's pervasive like electricity. By itself, it's not much of a science, but when it enables quite a few of these industries and domains and applications, just like electricity. By itself, fire or electricity doesn't do much, and has quite a few challenges like transportation and do pose danger, like fire can burn, and it's been there for almost 2,000 years. And so some of the dangers that these technologies have posed, AI comes with that too, and it's not anything new. It's been touted as a 4th industrial revolution. Railroad was first, assembly line was second when it connected the world, the US, the transportation of the goods was possible from one location to the other. And of course, digital. In 1970s, when chips started, the whole thing, changed our lives. So there are a lot of semiconductor powered devices that we are on today. We cannot realize our daily life without those. And 4th one is AI. On the right-hand side, you see, just few of these examples what AI would do to many of these industries. It's going to change them fundamentally, the way they operate, the way they work. And so it's fast becoming sort of central connect for the disruptive change around us. Anywhere from the user all the way to development and developers. Right? If you are writing software today, most likely 10 years from now, you'll be writing something in AI, some statistical approach to your program, which is part of a larger system. So software is also likely to change. I'm sure people here are smart enough to know the distinction, but in the media there is a lot of hype, and people do use these words interchangeably. For the lack of clarification, I would be using ML mostly. AI is a superset of that. DL and NN are a subset of machine learning, and there are other approaches that are nascent. To give you an idea, deep learning is growing at a phenomenal rate. Just the research part, in last 24 months, there are almost 100,000 papers. 100,000 papers just in deep learning. So research and academia is bubbling with the ideas, and still in the nascent stage. And it's not just the research or universities that are excited about this. The money that's thrown around on the technologies is phenomenal too. In last 12 months, and I'll talk about that in some of the slides too, just in last 12 months, June 2018 to June 2019, the influx of money in AI hardware startups, not applications, hardware, the kind of chips people are hoping to create, is about 7 billion in Bay Area. This is not worldwide, just in Bay Area. There are about 100 startups that are building some kind of hardware that is different from the other company. And not that we need 102 startups, but some of these ideas are out of the box. And 5 years from now, probably 5 or 10 will survive. Rest of them, like the startup world is, will unfold or will get acquired by a large player. But this kind of scale gives you an idea as to why there is so much hype around AI. And this slide talks about where is it going. By the way, so this talk is supposed to be conversational. I'm not the one to talk. So if you have a question or a comment, or if you have an experience, please do talk about that. Right? So this one is showing where AI is entering our lives. If you have one, probably you have multiple applications already that are powered using machine learning or some kind of deep learning application. And that's an old news. It's not something new. Your phones are very powerful CPUs and neural processing units combined. So your phone is not a weak device or a basic device. It's a pretty powerful device. So smart home. You have TV, likely it has some kind of machine learning in it. If you have purchased a refrigerator after 2015, a high-end one, likely it has something in there too. If you have watches, I can go on and on. If you have a toy, more than $20 or $50, likely it has something inside too. And it's actually getting more popularity inside industries where some of these applications that were done with the deterministic software, like finding if particular machine has a fault or it's operating normally, completely replaced in last 2 years. So every industry, whether it's oil, fintech, if it is operating on sensors, it is using machine learning. And the development is phenomenal. And it's not that it's creating a new industry by itself, it's changing the existing industries. And of course, smart cities. We all know connected cars, infrastructure, car talking to cars, car talking to hubs. The University of Arizona is putting in huge money. And Waymo, and there's one more car provider which is providing these free trips in the city from Walmart and some of these stores to your houses. And they are not charging anything for now. They are actually associating, they're charging, from the vendors because they are bringing customers from houses to Walmart or malls. So per customer, they're charging to the. So the business models are also evolving. Just on the car, there is a lot of controversy. There are a lot of opportunities. How that would evolve, and you can. Talk about from your experience. Anybody has any experience on the smart car, like how the insurance would work? And there is a very popular question that's around smart cars, which is posed more philosophically than as a reality, which is if a car sees a group of 10 people and it is on the cliff, it has only 2 choices, either run into the crowd of 10 people and kill all of them, or get on the cliff, or some other condition where the driver does not survive. What decision should it take? And there was a talk, very interesting talk in the University of Stanford, Stanford University, Professor Faisali, and non-technical professor from one of the European universities. The philosophical repercussions of these ideas and how that should shape the way we live today. It's going to impact no matter what. And they are very interesting questions. Either way, if you happen to decide that you would kill 10 people, the government and regulators would not release that, let you release the car. And If the car decides to kill the driver, nobody will buy the car. So either way, it's a difficult question. And there are a lot of interesting ideas and questions like that around AI.
But wouldn't the car companies or the car service industries spring up because they will control the cars rather than individual?
Right. Yeah. But some of these questions would have to answer by them as to what happens under this hypothetical scenario, right? And that comes from insurance industry, more from mere mortals like us, consumers like us. Insurance industry is very afraid of these cars. There are no models yet as to if the cars are in collision or somebody is killed, who is responsible? Is it the manufacturer, the driver, or somebody else, and where to put the blame and how to put the blame? So there are a lot of questions around that, and they've been there for almost 10 years now. But it's getting to a point because the technology is maturing, getting to a point where some of these questions are, taking roots and are seen more in the media. So I can go more and more on that, right? So pixel explosion, just on the vision, right? So here's the data. This actually slide shows how the sensors are growing. And on the right-hand side, the blue line shows number of image sensors that are produced every year. And the top blue line is the world population. And in 2013, there were about 2.6 billion image sensors that were produced every year. And today, our population this year is 7.7 billion, right? And why that comparison is interesting, it kind of compares as to how many sensors per person is consuming. And so that line in 2019 is about to surpass the population. Next year, we will produce more sensors than world population. And those sensors are becoming cheaper by the day. Now, why is that important to deep learning or vision? Every sensor is capturing something, some form of pixels, right? The data is being generated and consumed by a server either in the cloud or on the edge, right? So that sheer number on the right-hand side is your population, which is 2 billion, 4 billion, and up to 10 billion, right? And given that sensor's life is about 3 years, you can combine these three pillars and come up with sensors that are working today. So if you go by that number, the number of sensors have already surpassed human population. There are about 20 billion sensors that exist today worldwide, and this is almost every 3 per person. And so that's one stat. So the other stat is 99% of the entire data that internet consumes today is pixels. It's all sheer pixels. Rest is volume and the data. So given that, given we are producing so many sensors every year, and so much data is being produced, where is the limitation? And who's going to get hit, and how will this change the rest of the world and the way we live today? And this is calculation on just looking at the bandwidth. So this right-hand side is internet bandwidth. It's a Wikipedia article, and the bandwidth is in the petabytes per month, and it's roughly about 120 petabytes today from all sources. So given that, this translates to about 45 gigabytes per second. That's our internet. And if you see that all these sensors that are capturing these pixels, if they were to transmit somewhere on the internet, it would take 100 exabytes. And exabytes is about 10 to the power 18. So you see 45 gigabytes to 100 exabytes. We are order of magnitudes away. It's 10 to the power 10. And if we were to double our bandwidth every year, it will take 32 years to come up to what we need today. So this explosion, just the sheer number, kind of tells you that we are way behind for what is required. So if this number impresses you, you might wonder where would the bandwidth come from. This 5G is not enough. People are talking about 5G, right? I mean, it's going to enable this, enable that. It's nowhere close to what is needed today, based on just the sensors that we are producing. So bandwidth, if you combine the bandwidth offered by every network on this planet Earth, including 5G, still magnitudes away of the order less than what we need, just for vision. So what's going to happen? So immediate fallout is if you don't have bandwidth, you'll have to do some processing on the edge. And that's where the push to the edge coming from. And this is just one limitation that's pushing. There are other limitations too that are pushing this technology in the edge, where it has to be because there is no other way. And privacy is another issue where there are sources which are either not comfortable or not allowed to leak their device. So if you're capturing pictures and you don't want your pictures to be stored on any cloud, right? Some people would like their privacy, so you're not sharing that with anybody. That's another, and you still want your application to work and give you faces and recognize you. That means you have to do that processing in the device itself. And so the whole point I'm trying to bring here is there are several factors, several aggressors that are pushing AI to the edge. You have a comment, sir? Question? Okay. So like I said, it's just to foster conversation. And if you have any experience with that or know something you would like to share, please do speak up.
So I had an observation or kind of question. So Cisco says that because of the Internet of Things explosion or Internet of Everything, there'll be around 50 billion devices by the next year, to 2020. So I think that is still possible with the bandwidth. That's
no, probably Cisco would not say that, does it? It's not. So they're saying there would be 50 billion devices. I have something similar in the coming slide. So these devices, they won't talk to internet or to each other. Just imagine a farmer, right? The village does not have electricity today. And you would want that farmer to have some kind of application under $10 which it can carry around and find out if this plant is poisonous or not, or it's going to harm or not, things like that, right? Number of things you could do in farming. And there is a large industry developing applications for farmers. They will not be connected to the internet. So there will be devices, and that's another push that's coming. That until 2010, the term IoT came around 2009. A famous venture capitalist used that, and it's run out of its steam and the meaning. So there will be devices that will not be connected because of number of reasons. There is nothing that connects them. The application itself does not make sense to stay connected, or there is not enough processing power, or bandwidth, or privacy, and other things. So the devices are going to increase with AI, but they may not be connected. So that number is likely correct, but the connectivity is not certain. Any other observation?
So how do you think the edge devices will address this challenge of AI getting pushed to the edge? Because edge devices today, they're mostly CPU based, right? And they're not GPU based. So how do you think they will address that?
Right. So, one area that's picking up is how do you run these models with limited power and limited compute power running on batteries. Like I said, your phone is very powerful. It has GPU and everything. And Raspberry Pi, $30 device, has a GPU. I mean, most people do not know, even people who work on Raspberry Pi, it has a Broadwell GPU. But that's not what we're talking about here. We're talking about microcontrollers under $10. something that everybody already has. So back to your question, how would it address? So there is an industry, is push from large players as well as small startups on reducing these models, coming up with new technologies that run on these devices. And not everything requires GPU. For example, let's say this door, right? You want to find out if somebody entered through this door or not. 1 frame per 5 seconds is good enough, right? So you train the model using deep learning, like 3 or 5 layers, and you have a model which is looking at the door every 5 seconds and processing and counting. The door was opened so many times, right? And this is fairly good application if you want to deploy that in your household, right? Nobody should open the doors between 10 to 6 or 10 to 5 or whatever the time is. Otherwise, alarm goes off. Doesn't require any connectivity, no internet, very limited power. Does not have to be on the plug or connected. It works, right? So not everything is power hungry, as media and these companies who have their vested interest would like you to believe that, oh, everything needs to run into GPU. No. Cars probably do. They require about 10,000 frames per second. Number of reasons. They have 6 cameras. They're running at 60 miles an hour, high speed, right? So the processing power has to be there. But for something static like this, you don't need that. And let's say another application that I talked about, farmer carrying around the camera and the device. 1 frame per second, maybe 1 frame per 10 seconds is good enough, right? For him to just carry around. That doesn't require a GPU and huge processing power. Now people are realizing that and putting some of that to practice. So you see good push from NVIDIA, for example. They're releasing Jetson Nano, the family of edge products that are coming to the fore. Google is working on that, right? Google Core, another $10 device or something. So there are a lot of benefits and advantages and limitations on the edge processing, but it's not impossible as it was thought 2 years ago or even last year. Okay, so this slide shows just the sheer amount of opportunities that AI would bring. Now, how this plot is essentially the 50% is a collection of 12 countries that produce 50% of the entire world GDP. And so this study was done by Accenture in 2018 and compared the growth of GDP with and without AI. So baseline is your orange, where the country is growing at a certain rate, and how will it grow without AI and with AI. So if you happen to ignore the usage of AI in your industry, countrywide, this is a macro trend worldwide, then you are anywhere from 30% to almost 200% lower in your GDP. So countries like China are rushing. So if you see, China is not part of this, is it?
No.
I don't see it. Okay, so I have no idea why that study ignored China, but China is huge on AI, and they're deploying AI in daily lives to a point that there are concerns not only privacy, but they cross the UN guidelines. Like they're tracking their citizens and using this technology and know where everybody is to trace and locate their own citizens. And it's being used in some certain provinces more than others. And there are quite a few articles in the media. If you just search Google, you will find some.
What is the baseline here? What exactly does the baseline mean?
So baseline, so I have a reference, if you can quickly go on there. So this is a report, it's small report and large report. I think and so the reason I'm saying that is I am using my memory to give you the answer. I might be wrong. But this is 2.6.
Might be the GDP, the current GDP.
Current GDP. The numbers, is it trillions? It won't be trillions. US is about 25. So it's something else.
But the growth rate was,
It is, yeah.
it has been between 2 and 3, right?
So it is a growth
Last,
rate.
Oh,
quarters.
growth rate of the GDP.
Yeah.
Within that.
So with AI, it would have been 4.6.
4.6, yes.
How did they do the simulation?
So they have the entire report.
Oh.
So go to this link, that link will show you like 4 pages, and they have, the methodology they explain as to how they went into finding that. So every report has,
I don't think it is GDP rate, because Japan 0.8, it's unbelievable. United States 2.6.
yeah.
Trump is going to come after us.
Yeah.
I think it's much more.
No, it's between 2 and 3. It's been ranging that for last 8 to 12 quarters. It's been there almost like the entire 10 years. There have been only 2 or 3 overshoots of 3%.
Right. Yeah. So challenges in the edge, right? Opportunities, and of course it has challenges. Where do you get the power from? So the battery industry is growing, right? Now latency, not every application can be deployed. There are mission critical applications that will require certain frame rate, certain level of latency. You can't deploy those. And throughput, you need bandwidth and also processing power. If not one, can you put multiple microcontrollers inside one system? Is that a possibility? And then of course cost. Cost is a killer. You can't beat the cost. Microcontrollers are under $1. If you don't know, for example, Freescale uses ARM M0 Plus, which is 40 cents. Has about 32 kilobytes of memory and a processor that runs about 40 megahertz, which was a state of the art in '95. It's under $1 today, and of course privacy. Some application would require security, so that's a benefit for the edge processing. So this is only part of the ecosystem. It's growing at a much rapid pace since the beginning of this year. Every company that if it is working in AI, they would have some kind of strategy for edge and running it in edge, and how they are, whether it is Google, NVIDIA, AMD, a lot of startups, FPGAs, eFPGAs, and microcontrollers and everything in between. There are a lot of hardware companies that are showing up, and of course there are a lot of innovation that's going on in the hardware. Like I said, there are almost $7 billion that is being invested in just in the last year. Just in Bay Area, 102 companies that are doing something similar. And I'll talk about as to what makes sense where. Some of these companies, one company in particular, which is targeting, because all of this comes down to multiply and accumulate, and that's your adder for CPU. You have to bring in these two arguments for the adder, and then process it. Takes 1 cycle or 2 cycles. Now what they're doing is so the time it takes from RAM to CPU is huge, and further bringing the parameters from the disk to RAM is of the order of milliseconds, from RAM to CPU about a few microseconds, and then processing, right? So if you look at just the chain inside the system, the weakest link is your disk, which is taking 1,000 times more. So there are algorithms that are fetching these before, and so there are hardware that are being built on the algorithms that what is needed would be fetched 2 milliseconds before, so that it can process much faster, and so on. There is a huge literature that's, but the good point about that technology is they're doing addition using analog, and so their memory is one side your parameter, the other side is your weights, and it works just like memory in a few microseconds. So they're enabling that addition is in a matter of microseconds instead of milliseconds. So this is the landscape, and this was updated in August 2019, every company, every large company you can think of is there. There are a lot of startups, and this plot is, there's a reference, yeah. So there is a source there. If you go, they don't include anything less than 5 million or something. So you have to be above the range. And all of these are in the Bay Area. So you have giants like Google, which have software, hardware. They have spun up a company called Grok. You have NVIDIA, AWS, Amazon, IBM, name it, it's there. And most of that was happening in the cloud until last year. It's changing. So, and just to repeat myself, over $7 billion have been invested from June 2018 to June 2019 in AI hardware startups just in Bay Area. So this is subclass of a subclass of a subclass. It's not counting everything. Okay, I'm not going to go into this. So this is the anatomy of NPU, slightly more technical. Probably most of you know more than I do on this. But the point was to clarify the weakest link in the processing. It's not always about your GPUs and these scalars that are the vector arrays that are working together to give you the latency and throughput that you need. So this is from Google TPU, the basis of Google Coral. It's a chip that is released in open source. Now, why AI accelerators, right? So inferencing is easy, training is hard because of number of algorithms that are required additionally for training. Just on the vision side, the algorithms that are needed, and there's not one particular, for example, let's talk about convolution, right? Convolution is part of CNNs, which are very popular. I'm sure everybody in the room has heard there is some kind of CNN. And so if you have your phone, facial recognition using CNNs. And it uses convolution. Convolution is essentially multiplication and addition. So W times X plus B, that's your multiplier and adder right there. Now it's slightly more complex in hardware. Now the sizes, the way these matrices are combined, could be anywhere from 28 by 28 images up to 416 by 416 times 3 images. You may not realize, for human eye, it's a very small thumbnail kind of size, or quarter of your screen in the laptop. But for if you just count the number of pixels, it's about 40,000. So it's 40K, just one frame. Multiply that, and that gives you the scalability. So the challenges on that is parallelization of these models as and when it's coming. Real life, for example, cars, you need 10,000 frames per second. How do you get that kind of throughput? So these are very, very hard problems. And some of the companies are trying to change the model itself. There's one company in particular is hoping that these neural networks will change in the future, because that's not how the data is distributed. Their frame of thinking is data is distributed in a different manner than the way these guys are computing. So they are coming up with a new neural architecture and sort of hoping that it would pick up. But microcontrollers, again, edge enablers. Cost is a killer advantage. Nobody can beat under 10 or under $5. Privacy, your flexibility, low power, they're reliable. They've been there for over 40 years. They're everywhere. They are using OS, RTOS, or some of them are OS-less. They're so tiny that they don't even have OS. So that's one challenge. Now, why AI edge or microcontroller development or developing on microcontrollers did not pick up before, right? We don't see many developer kits around for microcontrollers other than from the vendors. Everybody uses C++, Python, those are popular languages, mostly deployed in servers and larger systems. So microcontrollers, okay. It's not showing up there.
Oh, your network is flaking.
Oh, yes.
That doesn't.
Okay. So the software support for that is still coming up, and new IPs and designs will enable new wave of application.
Can you just share again? You can go on Android.
So yeah, so the software support, you guys are done with your research. So let me finish it quickly. Software support is something that world is still catching up with, and slowly people are moving. And we at AI-TS are doing our part. We are developing a compiler which would work for these large models, and we'll try to come up with an executable that works on the microcontroller of your choice. I'm hoping at the end, before you leave, if you have a laptop and would like to try under a minute, there is a link. If you guys can go to bit.ly PNN compiler on your browser. So it's bit.ly /PNN compiler. So that's capital C with compiler. It'll take you to GitHub. It's an open source repository. bit.ly/DNN capital C compiler. Capital C. Yeah. So there in third or fourth link will give you a notebook. If you click on that, it'll open Google Colab, and all you have to do is just to run that application. No?
Yeah, the bandwidth doesn't seem to be high. So by the way, feel free to have some more slices of pizza. It's all vegetarian. Everything is not. So folks on the network, we're having some network issues with the phone.
So how many of you have found that link? It's a GitHub link. On the, let me see, on the second or third one, if you go down, oh, there you are already there. So if you go up, yeah. So try the first link.
But it's not running.
Right? So either you open it or you save it in your drive. So you can play now. Yeah. So it won't. So open that link and it will give you another window in your browser.
What is the network? How can I get into the network?
Lisa is watching. I'm connected.
You guys are connected?
He is not a Cisco.
He's a guest.
He's a guest.
Okay.
Oh, okay.
There's a guest here, but there is a way to generate a guest.
You could have a busy slice.
Oh.
It's like so if you launch the first link or you go to tutorial, I run the key and you might want to save it in the playground.
So there is separate code there. There is some.
I don't know which link to unmute. So if you want
Yes,
to
not restarting.
Yeah, it's not restarting. There is some
You have to go back.
dependency.
this one. So you change this to
No, that would be longer out. If you go down.
There is a dependency issue.
Yeah, the first link.
Yeah.
what is the intent of the?
Try deep sea.
Yeah.
What is deep sea?
It's a compiler. If you try deep sea, click on that.
Here?
Yeah.
So what is the intent of the compiler?
The intent of the compiler is, so this basically lets you try out things in Python because you have a huge system, right? If you end up writing an algorithm that you would like to port on your microcontroller, it has commands for that. So you write whatever you have. Generally, people either write their algorithm or they have Onyx model or TensorFlow model. So they have worked on larger GPUs. They have developed a model, 3 or 5 day worth of training. It takes that, understand it, and give you an executable. And it's called bundle because it has parameters and executables both combined. You can take that zip file and copy it in one of your microcontrollers or whatever device you have. And all you have to do is to run that. So run that exe and it's done.
So across platform,
It's cross.
can select the platform of the microcontroller.
Yes.
How does it know which underlying hardware it is?
Oh, you have to provide that. It's not that smart. So it worked for you?
There is some dependency here, it looks like.
Yeah.
I didn't know what I need to
So
check.
open in playground and do run.
So quick question, we are going to forward the slides to the team here who attended, right? The presentation slides?
Yeah, sure.
Okay, so in that, will it have this link?
Yeah, one slide does. One
Yeah?
slide
Okay.
does. Yeah. So if you are wanting to leave, you're welcome to leave. I didn't mean to keep you around. If you have questions and would like to talk, share your discussions. The whole idea that we are promoting is try it. It takes seconds. Get you started. If you have something interesting for your household, for your child's project, it lets you do that in minutes. You go down. No, not going to see. Okay.
Yeah, basically working.
Then there are these tutorials that.
So I have a question. Recently, I heard that Microsoft is trying to work with GraphCode, an AI chipset vendor, and they are deploying it on the cloud. And that a corresponding slave kind of chip would be running at the edge of the stack. That's what they are claiming to be. And the training would happen on the cloud, and the inference would happen on the edge. And it looks like that is meant for a similar use case what you are trying to do with this cloud platform.
No, ours is more focused. It's entirely on the edge.
Okay, nothing on the cloud.
Unless you want it. No. You will need more frills to be able to communicate that.
So even the training in the scenario, it happens at the edge.
Training, sometimes it's not possible, right? So somebody your laptop, that's powerful enough. If you leave it running for 12 hours, it will give you something, some trained model. So, okay, yeah. But microcontrollers are weak.
Yeah, imagine, let's take this use case scenario. You have PLC, and the PLC is made of microcontroller. I want to use this tool that you provided. You will not be able to train.
Not on PLC, no.
Not on PLC. So now, in the real-time use case scenario, what we have seen in the manufacturing,
Okay,
the PLC is connected to the cloud. The training happens on the cloud. Based on the incoming traffic, we extract the metadata, let's say Profinet or SCADA or whatever, the IoT data. Extract the metadata and use the cloud. Cloud does the processing and sets the action, only the inference happens at the edge. So in this use case scenario, let's say I select the PLC's microcontroller and I want to leverage this tool. How should I proceed?
So you will have to write on, once you get the executable and the bundle, you write another layer on top. Which, yeah, something in Python or C++ or whatever is the choice, your choice of language, and get the data and then so that's essentially you learn to code it up.
So let us close it formally,
Yeah.
and then you can take informal discussions.
Thank you.
Ready for the photo?
Oh,
Official.
yeah. And if you are interested and would like to reach out, I will provide my links. I am always, available for people who would like to try something new. for your child. These things are becoming very popular, right? My kids, my younger one is writing a small compiler. So in high school, writing these applications is not enough. So it's getting to a point where even in high school, they're not accepting application. So sixth grade, eighth grade, ninth grade, if you have a child who's looking to develop something, feel free to reach out to us. We would love to help. You have this repository. My email is rohit@AI-TechSystems.com, or my personal email is srohit@gmail.com. Would love to help using this. So, and if you would like to learn, feel free to reach out. We have a community of developers. This is not just AITS. AITS is providing certain funds, and